Picture this: a star, billions of times brighter than our sun, suddenly explodes in a cataclysm so violent it outshines entire galaxies. For a brief, terrifying moment, it unleashes more energy than our star will produce in its entire lifetime. This is a supernova, just one of the universe's many harbingers of destruction. But what if I told you there are far more terrifying things lurking in the cosmic dark? Objects so powerful, so incomprehensibly deadly, they could erase worlds in the blink of an eye. Today, we're diving into the 25 most dangerous objects in the universe, entities that defy imagination and rewrite the laws of physics with their sheer destructive might. From black holes that warp spacetime itself to rogue planets hurtling through the void, the cosmos is filled with phenomena that inspire equal parts awe and dread. Imagine a quasar, a supermassive black hole's feeding frenzy, blasting out jets of energy so intense they could sterilize entire galaxies. Or neutron stars, city-sized corpses of dead suns, spinning faster than a kitchen blender and crushing matter into oblivion. These aren't just abstract concepts, they're real, active threats lurking in the void, reminders of how small and fragile we truly are in the grand scheme of things. But this journey isn't just about fear, it's about wonder. Each of these cosmic monsters holds secrets that challenge our understanding of reality. What happens when a star gets too close to a black hole? How does a gamma ray burst, nature's most violent explosion, form? By the end of this exploration, you'll not only grasp the sheer scale of these terrifying objects, but also appreciate the bizarre beauty of the universe's most extreme phenomena. So buckle up, we're about to venture into the darkest, most exhilarating corners of space, where the laws of physics twist into nightmares and where every discovery leaves us breathless. Deep in the heart of our galaxy, a monster lurks: Sagittarius A, a supermassive black hole with the mass of 4 million suns squeezed into a space smaller than our solar system. Black holes are the ultimate cosmic predators, born from the corpses of massive stars that collapsed under their own gravity. When a star at least 20 times heavier than our sun exhausts its fuel, it doesn't fade quietly. It implodes with such force that not even light can escape its grasp. The boundary marking this point of no return is called the event horizon, a one-way ticket to oblivion where the laws of physics as we know them break down completely. Approach too close and you'll experience something bizarre and horrifying: spaghettification. The black hole's gravity is so strong that it stretches anything, stars, planets, even atoms, into long, thin strands like cosmic noodles. In 2019, astronomers witnessed this brutal process firsthand when a star ventured too near a black hole 21 million light-years away. Over months, the black hole shredded it, swallowing some of the stellar material and flinging the rest into space in a fiery, swirling disk. But black holes don't just destroy, they twist the very fabric of reality. Their immense gravity warps spacetime itself, bending light and slowing time to a crawl near their event horizons. Picture throwing a clock into one. From a safe distance, you'd see its hands freeze as time stretches infinitely. Yet even these cosmic titans have a flaw: Hawking radiation. Proposed by physicist Stephen Hawking, this faint glow of particles escaping a black hole's grip means they aren't eternal. Over unimaginable eons, they slowly evaporate, leaking energy back into the universe. From devouring stars to bending the rules of existence, black holes are nature's most terrifying enforcers, proof that in the universe's grand arena, not even light gets out alive. Imagine taking a star twice as massive as our sun and crushing it down until it's smaller than a city. That's the terrifying reality of a neutron star. These cosmic remnants are born from the violent death throes of massive stars, collapsing under their own gravity after a supernova explosion. What's left isn't just dense, it's incomprehensibly so. A single sugar cube-sized piece of neutron star material would weigh as much as Mount Everest, compressing more mass than you could wrap your mind around into a space no wider than a football field. But the horror doesn't stop there. Neutron stars spin at dizzying speeds, some rotating hundreds of times per second. That rotation, combined with their mind-bending magnetic fields trillions of times stronger than Earth's, creates one of the deadliest phenomena in the universe, pulsars. Picture a lighthouse, but instead of gentle beams guiding ships, it's blasting out concentrated radiation that could vaporize anything in its path. These cosmic death rays sweep across space like an unrelenting scythe, sterilizing planets or shredding molecules in their way. In 2004, astronomers witnessed the aftermath of a pulsar's wrath when a beam from one named Pulsar Bone 1750-24 sliced through a nearby gas cloud. The energy released was equivalent to detonating a nuclear bomb over every square inch of the cloud's surface. Even more chilling, some neutron stars called magnetars have magnetic fields so intense they can distort atoms from thousands of light years away. A flare from one in 2004 briefly outshone our entire galaxy, scrambling satellites and flooding Earth's upper atmosphere with X-rays. Yet, for all their destructive potential, neutron stars are also cosmic laboratories. Their extreme conditions let scientists test the limits of physics, from how matter behaves under crushing pressure to the nature of gravity itself. They're reminders that even in death, stars continue shaping the universe, sometimes as silent corpses, other times as raging beacons of annihilation. If neutron stars are the universe's undead monsters, then magnetars are their berserker cousins, neutron stars dialed up to 11. These cosmic anomalies take the already extreme physics of their kin and crank the nightmare factor to unimaginable levels. Picture a magnetic field so powerful it could wipe your credit card from halfway across the galaxy. That's not science fiction, it's the reality of magnetars, where magnetic forces reach a staggering quadrillion times stronger than Earth. To put that in perspective, if a magnetar floated as close as the moon, its pull would rip the iron from your blood long before tidal forces tore you apart. The true terror of these objects isn't just their strength, it's their volatility. Magnetars are cosmic pressure cookers, their crusts constantly cracking under the strain of those insane magnetic fields. When these starquakes happen, they unleash bursts of energy so intense they rewrite the rules of astrophysics. Take December 27, 2004. A magnetar named SGR 180620, located 50,000 light-years away in the constellation Sagittarius, erupted without warning. In 0.2 of a second, it released more energy than our Sun has emitted in the last 250,000 years. The gamma-ray blast was so powerful it ionized Earth's upper atmosphere, disrupting radio communications and satellites. A stark reminder that even at interstellar distances, magnetars demand respect. But what if one lurked closer? A magnetar within just 10 light-years would be an existential threat. Its periodic flares would act like cosmic sandblasters, stripping away planetary atmospheres and sterilizing any world in their path. No ozone layer could withstand that assault. No life as we know it would survive. Even more chilling, some researchers theorize that magnetar outbursts could be behind mysterious extinctions in Earth's past. While we've been lucky so far, the universe has over 30 known magnetars, and statistically, at least one should erupt every few million years in our galactic neighborhood. Yet for all their destructive potential, magnetars are also cosmic gold mines for scientists. Their extreme conditions let us study matter in states impossible to replicate on Earth, probing the limits of quantum physics and the nature of magnetic fields themselves. They're reminders that the universe doesn't just harbor beauty, it wields forces so raw and unfathomable that even a flicker from one of these stellar nightmares can echo across millennia. Next time you gaze at the stars, remember, somewhere out there, a magnetar is winding up for its next cataclysmic tantrum, and the universe is holding its breath. Rogue black holes are the universe's perfect predators, silent, invisible, and utterly merciless. Unlike their supermassive cousins anchored at the centers of galaxies, these lone wanderers have been violently ejected from their cosmic homes, set adrift in the darkness between stars. Picture a black hole millions of times heavier than our sun, hurtling through space at staggering speeds, completely undetectable until it's too late. No glowing accretion disk, no telltale flares of devoured matter, just pure gravitational malice cloaked in nothingness. The birth of a rogue black hole is as violent as its future is ominous. When galaxies collide, the titanic gravitational tug of war can fling black holes clear into intergalactic space like cosmic billiard balls. Some might even be primordial black holes forged in the chaos of the early universe, lurking unseen for billions of years. The terrifying truth, there could be hundreds of millions of them drifting through our galaxy right now, passing unseen through the voids between stars. Now imagine one slipping into our solar system unnoticed. Its gravity would warp planetary orbits long before we ever saw it coming. Neptune's path might suddenly wobble. The asteroid belt could scatter like shrapnel. By the time Jupiter's orbit stretched unnaturally, the black hole would already be close enough to start dismantling our cosmic neighborhood, swallowing planets one by one. There would be no fiery explosion, no dramatic collision, just cold, silent oblivion as worlds vanished without a trace. Astronomers call this a flyby disaster, and it's not just theoretical. In 2012, researchers simulated a rogue black hole passing through our solar system. The results were chilling. Even a distant encounter could fling Earth into a deadly elliptical orbit, triggering extreme seasons that would devastate ecosystems. A closer approach unthinkable. The black hole's tidal forces would shred our planet apart long before it could swallow us whole. But here's the twist: rogue black holes might also be cosmic architects. Some scientists speculate they could seed new star formation, their gravity compressing interstellar gas into nurseries for future suns. Others suggest they may explain dark matter, their unseen mass shaping the universe in ways we're only beginning to grasp. It's a haunting duality. They could annihilate worlds or perhaps unknowingly help create them. So while we scan the skies for asteroids and supernovae, the true dark horse of cosmic doom might already be gliding toward us, invisible and unstoppable. The universe doesn't need flashy explosions to end a world. Sometimes all it takes is the quietest predator, a shadow with an appetite. Some stars don't just burn, they race. Hypervelocity stars are cosmic fugitives, hurled through space at speeds exceeding 1,000,000 miles per hour, fast enough to cross the entire United States in less than a second. These aren't gentle wanderers, they're galactic bullets ejected by the universe's most violent slingshot, supermassive black holes. When a binary star system drifts too close to a black hole's gravitational maw, one star may be devoured while the other is flung away at unimaginable speeds, a singular survivor of a celestial catastrophe. The energy behind these ejections is staggering. Astronomers have clocked hypervelocity stars moving at over 2 million miles per hour, so fast they're not just escaping their home galaxies, they're punching through the fabric of intergalactic space itself. Take star HVS 17, for example. Discovered in 2005, it's streaking toward the void at 1.6 million miles per hour, leaving the Milky Way behind forever. Imagine the force required to launch a 1,000,000-mile-wide ball of plasma faster than a speeding bullet. It's like kicking a cannonball into orbit. Now picture one of these stellar missiles barreling into our solar system. Even at a distance of a few light years, its gravity would wreak havoc. Planets would shudder in their orbits, their delicate gravitational harmony thrown into chaos. Neptune might spiral into the freezing outer dark, while Earth could be shoved closer to the sun, scorched into a wasteland, a direct hit unthinkable. The collision would unleash energy rivaling a supernova, igniting planetary atmospheres like matchsticks and reducing worlds to molten slag. Yet hypervelocity stars aren't just agents of destruction, they're also cosmic breadcrumbs. Their trajectories trace back to the black holes that spat them out, offering astronomers a way to map these invisible monsters. Some might even carry planets in tow, rogue worlds surfing the wake of their runaway suns. It's a haunting thought. Entire civilizations, if they existed, could be adrift in the abyss, their home stars long gone, their futures written in the dark. So while we gaze at the night sky's seemingly fixed tapestry, remember, some stars are anything but still. They're the universe's shrapnel, remnants of ancient violence, and proof that even in the vast quiet of space, nothing truly stands still. At the heart of distant galaxies, engines of unfathomable power rage quasars, the brightest and most violent objects in the universe. These aren't just distant specks of light. They're supermassive black holes gone berserk, gorging on stars and gas with such ferocity that they outshine every star in their host galaxy combined. Think of a black hole not as a passive vacuum but as a cosmic hurricane, its swirling accretion disk heating matter to millions of degrees before devouring it. The energy released in this frenzy doesn't just vanish, it's funneled into twin jets of plasma, narrow and precise as laser beams, screaming across space at nearly the speed of light. These jets can stretch for millions of light years, longer than the distance between galaxies, carving through the cosmos like celestial blowtorches. What makes quasars truly terrifying isn't just their scale, it's their reach. A quasar's jet pointed at Earth would be an extinction-level event unlike any other. In 2003, astronomers observed one such jet from quasar 3C 273, blasting through intergalactic space with enough energy to vaporize atmospheres and strip planets bare. The radiation alone would bombard any world in its path with X-rays and gamma rays, scrambling DNA and boiling oceans in an instant. And here's the chilling part, quasars aren't rare. Billions of them lit up the early universe, their light just now reaching us, a graveyard of galactic-scale destruction frozen in time. Yet quasars aren't just agents of chaos, they're also cosmic lighthouses. Their brilliance allows astronomers to map the universe's structure, illuminating the vast webs of gas and dark matter that bind galaxies together. Some researchers even believe quasars played a role in shaping the cosmos, their jets seeding future star formation by compressing interstellar gas. It's a paradox. These ancient death rays might have paved the way for life, their destruction birthing new possibilities. So when you look up at the night sky, remember, some of those faint points of light are monsters in disguise, their fury quieted only by the immeasurable gulf of time and space. The universe doesn't just create, it consumes, reshapes, and reinvents itself in cycles of violence we're only beginning to understand. Gamma-ray bursts are the universe's ultimate flashbang, cosmic detonations so bright they outshine entire galaxies for a few fleeting seconds. These aren't just explosions, they're focused death beams, narrow jets of energy erupting from collapsing stars or colliding neutron stars, packing more power than our sun will emit in its entire 10 billion-year lifetime. The sheer scale is incomprehensible. In 10 seconds, a single gamma-ray burst can release as much energy as a supernova, but funneled into two tight streams traveling at 99.99% the speed of light. Now imagine one of those beams aimed directly at Earth. In 1999, astronomers witnessed a chilling preview. A burst designated GRB 990123 erupted 8,000 light-years away, its gamma rays flooding our solar system with radiation. Had it been pointed at us, the effects would have been apocalyptic. The initial blast would have stripped our ozone layer within seconds, bathing the planet in lethal ultraviolet radiation. Skies would ignite in artificial auroras as atmospheric nitrogen fused into toxic compounds, raining acid down on every continent. Fossil records suggest this might have happened before, Some scientists theorize a gamma-ray burst triggered the Ordovician extinction 450 million years ago, wiping out nearly 85% of marine life in a geological instant. What makes these bursts truly terrifying is their unpredictability. Unlike supernova, which build to a crescendo over weeks, gamma-ray bursts strike without warning. By the time telescopes detect the first photons, the devastation has already begun. The closest known candidate, WR-104, sits just 8,000 light-years away, a stellar time bomb with a 50-50 chance of aiming its death beam our way when it collapses. There's no shelter, no advanced warning system, just the cold statistical reality that somewhere, right now, a star is priming itself to unleash a blast that could sterilize half the galaxy. Yet gamma-ray bursts aren't just agents of destruction, they're also cosmic signposts. Their afterglows illuminate the distant universe, helping astronomers map the distribution of matter across billions of light-years. Some researchers even speculate they could have seeded the early universe with heavy elements, their fury forging the building blocks of future planets. It's a haunting duality. The same force that could erase all life might have also made our existence possible. So while we track asteroids and solar flares, the real existential threat might be a flicker of light arriving without warning, a final message from a dying star written in gamma rays and delivered at light speed. The universe doesn't care about fairness. Sometimes annihilation is just a question of being in the wrong place at the wrong time. When a massive star reaches the end of its life, it doesn't fade quietly. It throws a tantrum that can be seen across the universe. A supernova is the ultimate cosmic fireworks display, a detonation so violent it can outshine entire galaxies for weeks. But behind that brilliance lies raw, unfiltered destruction. These explosions aren't just spectacles, they're stellar apocalypses capable of sterilizing entire star systems in an instant. The death throes begin deep in the star's core. When fusion can no longer withstand gravity's crushing grip, the core collapses in less than a second, rebounding with a shockwave that rips the star apart from the inside out. The energy released is staggering, equivalent to detonating 10 octillion nuclear bombs simultaneously. For perspective, that's a 1 followed by 28 zeros. The outer layers are blasted into space at 20,000 miles per second, a storm of molten metal and radioactive debris that bulldozes everything in its path. Any planet within 50 light-years will be bathed in lethal radiation, its atmosphere shredded by X-rays and its surface scoured by high-energy particles. Earth's ozone layer would vanish overnight, exposing all life to the sun's unforgiving ultraviolet fury. History offers chilling examples. In 1054, a supernova erupted in the constellation Taurus, blazing so brightly it was visible in broad daylight for 23 days. Chinese astronomers called it a guest star, but there was nothing hospitable about it. If that explosion had occurred just 30 light-years closer, our planet would have faced mass extinctions. Even more sobering, the remnants of that very supernova, the Crab Nebula, still pump out enough X-rays to fry any hypothetical planets nearby. Yet supernovas aren't just destroyers, they're cosmic recyclers. The iron in your blood, the calcium in your bones, these elements were forged in stellar explosions long before our sun ignited. Every heavy atom on Earth was once hurled into the void by a dying star's final breath. It's a brutal cycle, death feeding new life, annihilation birthing possibility. So while we marvel at these titanic explosions from a safe distance, remember, the universe writes its history in fire and ashes. A supernova isn't just a star's end. It's the universe's way of scattering the seeds for whatever comes next. Two neutron stars spiral toward each other in a deadly dance, each one packing more mass than our sun into a city-sized sphere. As they draw closer, their immense gravity distorts spacetime itself, whipping up gravitational waves that ripple across the cosmos at light speed, then collision. The impact is so violent it briefly outshines 100 galaxies, forging gold, platinum, and other heavy elements in its wake while unleashing a lethal cocktail of gamma rays and cosmic radiation. This is a kilonova, one of the universe's rarest and most catastrophic events. The discovery of kilonovas rewrote our understanding of cosmic alchemy. For decades, scientists puzzled over where heavy elements like gold originated until August 17, 2017. That's when gravitational wave detectors picked up the telltale tremors of two neutron stars merging 130 million light-years away. Telescopes worldwide swiveled to catch the aftermath, witnessing a flare of light rich with spectroscopic fingerprints of freshly minted gold. Calculations revealed this single event produced over 10 Earth masses of the precious metal alone, scattering it into space like cosmic shrapnel. Suddenly, the universe's treasure chest had its architects, neutron star collisions. But kilonovas aren't just celestial forges, they are also doomsday machines. The collision's gamma-ray burst would sterilize any planet within 1,000 light-years, its radiation shredding DNA faster than evolution could adapt. Even more chilling, the gravitational waves from these mergers twist spacetime with such force that, up close, they'd stretch and compress matter like putty. Imagine a ripple passing through our solar system. Planetary orbits would warp unpredictably, moons might be torn from their hosts, and Earth's crust could buckle under the strain. What makes kilonovas uniquely terrifying is their duality. They create the very elements that make life possible while simultaneously wielding forces capable of erasing it. The gold in your wedding ring, the uranium fueling nuclear reactors, these materials were born in seconds of unimaginable violence, remnants of stellar corpses colliding eons ago. It's a sobering thought. The universe builds and destroys in the same breath, its most generous moments inseparable from its most ruthless. Yet for all their destructive power, kilonovas offer something priceless: clarity. Each detection peels back another layer of cosmic mystery, from the origins of heavy elements to the behavior of matter under extreme pressures. They're reminders that even in the darkest corners of space, cataclysm and creation are bound together, two sides of the same coin minted in the fires of colliding stars. Surrounding every galaxy, an invisible fist grips the stars' dark matter halos, vast cocoons of mysterious mass that dictate the very rhythm of cosmic motion. Unlike the glittering spiral arms we see in telescope images, these halos are utterly dark, detectable only by how they bend space itself, forcing stars to whip around galactic centers at speeds that defy Newton's laws. Without their gravitational anchoring, galaxies would fling themselves apart, yet their true nature remains one of physics' greatest enigmas: particles that refuse to interact with light, slipping through our detectors like ghosts. The scale of these halos is almost beyond comprehension. Take the Milky Way. Our familiar pinwheel of stars is just the glittering core of a shadowy leviathan. Its dark matter halo stretches 10 times farther than the visible disk, a sphere of unseen mass weighing as much as 2 trillion suns. Picture a hurricane with winds of pure gravity, its vortex stretching across millions of light-years, sculpting entire galactic clusters into delicate filaments. Astronomers call this the cosmic web, a labyrinth of dark matter threads where galaxies cluster like dewdrops on a spider's silk. Now imagine one of these dark matter currents passing straight through you right now. Billions of these particles stream through Earth every second, their collective mass so diffuse they barely leave a trace. But what if they weren't always so quiet? Some theories suggest dense clumps, dubbed dark matter hurricanes, could occasionally whip through our solar system. These rogue waves would pack enough gravitational punch to subtly tweak planetary orbits or even heat Earth's core through friction, a silent storm with invisible consequences. The most unsettling possibility: dark matter might not be entirely inert. Hypothetical particles called WIMP, weakly interacting massive particles, could occasionally collide with ordinary atoms deep underground. Experiments like Xenon and LUX hunt for these phantom impacts in vats of ultra-pure liquid, waiting for a flicker of light that could rewrite physics. Other models propose even wilder ideas: actions, primordial black holes, or an entire dark sector of particles mirroring our own. Yet for all their elusiveness, dark matter halos are the universe's unseen architects. Their gravity laid the blueprint for galaxies to form, their tendrils guiding the birth of stars and planets over billions of years. They're the scaffolding behind the glitter, the silence beneath the symphony. Every time astronomers measure a star moving too fast or a galaxy bending light strangely, they're brushing against the fingerprints of this invisible giant. The cosmos isn't just what we see. It's what we can't. A reminder that the most powerful forces often leave the faintest traces. Drifting through the endless dark between stars, rogue planets are the universe's abandoned orphans, worlds torn from their suns and cast adrift in perpetual night. These frozen nomads don't orbit stars. They roam the cosmos alone, untethered by gravity's embrace. Some are ice-locked wastelands, their surfaces colder than Pluto's heart. Others might hide subsurface oceans, kept liquid by the crushing weight of their own atmospheres, their unseen depth swirling with mysteries. But don't mistake their solitude for harmlessness. A rogue planet isn't just a wanderer. It's a gravitational wrecking ball in slow motion. Picture one drifting into our solar system unnoticed. Even a small rogue planet, no bigger than Mars, could unleash chaos with a single gravitational nudge. Its invisible pull would ripple through the delicate balance of our planetary orbits, like tossing a bowling ball into a house of cards. Jupiter's massive gravity might shield us, or amplify the disruption, slingshotting the intruder deeper into our cosmic neighborhood. Earth's orbit could stretch into a deadly ellipse, swinging us closer to the sun's inferno before flinging us back into deep freeze, turning our climate into a pendulum of extremes. And if the rogue planet passed too close, the tidal forces alone would trigger earthquakes and volcanic eruptions on a scale we've never witnessed, cracking continents like eggshells. What makes these rogue worlds so unsettling is how common they might be. Astronomers estimate there could be billions of them lurking in our galaxy, outnumbering stars by at least 2 to 1. Some were likely ejected during the violent birth of their star systems, flung into the void by gravitational tug of wars between sibling planets. Others might be the corpses of failed stars, brown dwarfs too small to ignite fusion but too massive to belong anywhere. Yet here's the twist: rogue planets could also be dark arcs. In their subsurface oceans, shielded from the vacuum of space by miles of ice, microbial life might cling to existence, a testament to life's stubbornness. Some scientists even speculate that these drifters could spread life between stars, ferrying extremophile bacteria across the galaxy like cosmic pollinators. So while we scan the skies for asteroids and comets, the real existential threat, or perhaps opportunity, might be a silent world gliding toward us, invisible until it's too late. The universe doesn't just build and destroy, it exiles. And somewhere in the dark, a rogue planet is drifting, carrying either ruin or revelation, or both. White dwarfs are the universe's silent stalkers, stellar embers that refuse to burn out quietly. These dense remnants, the cooling cores of dead stars, pack a sun's worth of mass into an Earth-sized sphere, creating gravitational fields so intense that a teaspoon of their material would weigh as much as an elephant. But don't let their faded glow fool you. Beneath that calm exterior lies a potential for destruction so precise it's used to measure the cosmos itself. The danger emerges when a white dwarf isn't alone. In binary systems, these dead stars can siphon gas from a living companion, slowly adding stolen mass to their own. For decades, this cosmic theft might seem harmless until the white dwarf reaches a critical tipping point. At 1.4 times the sun's mass, the pressure in its core reignites carbon fusion in a runaway chain reaction. Within seconds, the entire star detonates in a Type Ia supernova, an explosion so uniform and bright it outshines entire galaxies. Astronomers call these events standard candles because their consistent luminosity lets them measure vast cosmic distances. But for any nearby system, that same precision spells doom. Imagine a white dwarf detonating just a few dozen light-years away. The blast would flood our solar system with X-rays and gamma rays, stripping Earth's atmosphere like sandblasting paint off a wall. The ultraviolet flash alone would ignite global wildfires, while cosmic rays would mutate DNA at a cellular level. In 2008, researchers calculated that a Type Ia supernova within 33 light-years would have a 50% chance of triggering a mass extinction. The chilling part, there are at least 14 white dwarfs lurking within that range right now, any one of which could go critical if paired with the wrong stellar partner. Yet these ticking time bombs also illuminate the universe's deepest mysteries. Because they always explode at the same mass, Type Ia supernovas helped reveal dark energy's existence in 1998, proving the universe wasn't just expanding, it was accelerating. They're the ultimate paradox, tools for discovery and engines of annihilation. They're light carrying secrets of cosmic fate even as it erases solar systems. So while white dwarfs might seem like harmless relics, they remind us that death in space isn't always violent chaos. Sometimes it's a slow, calculated theft, a quiet star biding its time until it steals just enough to rewrite the sky. Brown dwarfs are cosmic paradoxes too massive to be planets, yet too small to be true stars. These failed stars never quite achieved the nuclear fire needed to ignite hydrogen fusion in their cores, leaving them in perpetual twilight. But don't let their dim glow fool you. What they lack in stellar ambition, they make up for in sheer, volatile fury. Trapped between star and planet, they wield magnetic fields that put Jupiters to shame and radiation belts that could cook any nearby world to a crisp. Take the brown dwarf LSR J1835 plus 3259, discovered in 2015. Despite its surface temperature barely reaching that of a campfire around 1,800 degrees Fahrenheit, it hosts an aurora so powerful it outshines Earth's northern lights by millions of times. These aren't gentle celestial curtains, they're storms of charged particles accelerated by magnetic fields 1,000 times stronger than our Sun's. Any planet orbiting too close would be bombarded by relentless radiation, its atmosphere ionized into oblivion. What makes brown dwarfs especially treacherous is their unpredictability. Unlike stars, which stabilize after formation, these objects are cosmic adolescents trapped in perpetual tantrums. Their turbulent atmospheres churn with hurricane-force winds, while their magnetic fields twist and snap like rubber bands, unleashing flares of X-rays and radio waves. In 2020, astronomers observed one named WISEJ 0855-0714 spewing a flare so violent, it briefly outshone the brown dwarf itself, a tantrum visible across interstellar space. Yet the true danger lies in their invisibility. Brown dwarfs emit little visible light, lurking in the dark like stealthy assassins. Some could drift terrifyingly close to our solar system without detection, their gravitational pull subtly disrupting the Oort cloud and flinging comets inward. A rogue brown dwarf passing within a light year might not scorch us with radiation, but it could trigger a comet storm lasting millennia, turning our cosmic neighborhood into a shooting gallery. But here's the twist, these failed stars might also hide secrets to life survival. A few rare brown dwarfs, like those in the TRAPPIST-1 system, orbit at just the right distance to host temperate, rocky worlds. Shielded by thick atmospheres, such planets might endure the radiation, their skies perpetually lit by the eerie glow of auroras. It's a haunting thought that life, against all odds, could cling on in the shadow of a star that never was. So while brown dwarfs might not burn bright, they burn unpredictable. They're the universe's cosmic wildcards, reminding us that sometimes the quietest objects wield the most surprising power, and that failure in the grand scheme of things can still be spectacularly deadly. Hidden in the fabric of reality itself, cosmic strings are scars from the universe's violent birth, one-dimensional cracks in spacetime so dense, a single inch could weigh more than Mount Everest. These theoretical relics, born during the cosmos's first chaotic moments, aren't just oddities. They're potential doomsday machines strung across the universe like razor-wire traps left over from creation. Picture a crack in ice, but instead of freezing water, it's a flaw in the very structure of existence, a wrinkle in reality so extreme it bends the rules of physics around it. The danger lies in their instability. A cosmic string under tension doesn't just sit quietly, it vibrates, whipping through spacetime at near light speed. When two strings cross or a loop snaps, the energy released could dwarf entire supernova, not in a fiery explosion, but in a silent rupture of spacetime itself. Astronomers calculate that a single snapping string might unleash a burst of gravitational waves powerful enough to distort matter thousands of light-years away, compressing and stretching planets like putty. Even more unsettling, if a string passed through Earth, its gravitational footprint would slice cleanly through the planet, leaving two perfectly sheared halves held together only by habit until the slight offset in their orbits tore them apart over centuries. But cosmic strings could also be the universe's ultimate cheat codes. Their extreme density might warp spacetime into closed time-like curves, theoretical pathways to time travel. A pair of strings moving parallel at near light speed could create a time machine of sorts, bending the fabric of reality so severely that the end of the string loop would reconnect to its own past. It's a chilling thought. These ancient defects might not just destroy worlds, but unravel causality itself, turning history into a tangled knot of rewritten events. The hunt for cosmic strings is a detective story spanning the cosmos. Astronomers search for their fingerprints in the cosmic microwave background, telltale temperature spikes that might mark where a string's gravity lensed ancient light. Others scour pulsar timing data for abrupt glitches, potential evidence of a string's gravitational wake passing through. So far, no definitive proof exists, but the search continues. After all, finding one would be like uncovering a fossil from the universe's first trillionth of a second, a relic from before atoms, before light, before time as we know it had even settled into its rhythm. What makes cosmic strings uniquely terrifying isn't just their power, it's their permanence. Unlike black holes or neutron stars, these defects don't evaporate or fade. They could outlast the universe itself, drifting through the heat death of everything, silent witnesses to the end of time. And if just one exists within our cosmic neighborhood, it's a reminder that the universe doesn't play by safe rules. Somewhere out there, a thread thinner than an atom might be vibrating, waiting to snap and rewrite reality in an instant. The universe might be sitting on a quantum time bomb, one that could rewrite reality itself in the blink of an eye. This nightmare scenario is called vacuum decay, and it hinges on a terrifying possibility. What if the fabric of space isn't in its true stable state? Think of the Higgs field, the invisible energy field that gives particles their mass like a valley. Right now, we're in the lowest point, the true vacuum. But there could be a deeper valley, a lower energy state the universe should occupy. If a tiny patch of space somehow tips into that lower state, it would trigger a catastrophic domino effect, a bubble of true vacuum expanding outward at the speed of light, rewriting the laws of physics as it goes. Inside that bubble, reality as we know it would cease to exist. Fundamental forces might reconfigure instantly. Atoms could unravel, their binding forces suddenly incompatible with existence. Even spacetime itself might twist into new, unrecognizable geometries. The worst part, there'd be no warning. The bubble's boundary would move too fast for light or information to outrun it. One moment, everything's normal. The next, an inescapable wall of annihilation. Here's where it gets even more unsettling. This collapse could already be underway somewhere in the cosmos. A high-energy particle collision, a random quantum fluctuation. even the act of measuring a quantum system might theoretically trigger the shift. And because the bubble expands at light speed, we'd never see it coming. The first sign of doom would be the edge of the bubble itself, washing over Earth like an invisible tide, erasing chemistry, life, and even time in an instant. Yet vacuum decay isn't just science fiction. The math checks out. In 2012, researchers at the University of Southern Denmark calculated that the Higgs field's current state is metastable for now, but not necessarily forever. Particle colliders like the Large Hadron Collider hunt for clues, probing whether we're perched precariously on the edge of existential collapse. But here's the twist: if the universe is truly this fragile, why hasn't it happened already? One theory suggests the cosmos is so vast that these bubbles do form just far enough apart that they haven't reached us yet. Another proposes that the energy barrier to trigger decay is so high that it's practically impossible. Or maybe we're wrong entirely and the universe is safer than we fear. Either way, vacuum decay forces us to confront an uncomfortable truth: the universe doesn't owe us stability. The same quantum fields that allow stars to shine and life to exist might also harbor the seeds of their own destruction. It's a reminder that beyond black holes, beyond gamma-ray bursts, the ultimate danger might not come from any object, but from the silent, invisible fabric of reality itself waiting to snap. Wormholes tantalize us with the promise of interstellar shortcuts, tunnels through spacetime that could connect distant corners of the universe in an instant. While science fiction paints them as smooth, stable gateways, the reality would be far more terrifying. Real wormholes, if they exist at all, would be cosmic funhouses of chaos, held open only by a theoretical substance called exotic matter, material with negative energy density that defies gravity. Without it, these tunnels would snap shut faster than you could blink, crushed by the relentless weight of spacetime itself. Imagine stepping into a wormhole without enough exotic matter to stabilize it. The walls of the tunnel would collapse like a black hole's event horizon, spaghettifying anything inside into an infinitely thin stream of atoms. But even if you somehow kept it open, the journey would be anything but safe. Wormholes are thought to be riddled with Cauchy horizons, points where predictability breaks down entirely. Pass through one, and you might emerge in the wrong era, stranded millions of years in the past or future. Worse, some models suggest the very act of sending matter through could trigger a runaway feedback loop of radiation, vaporizing the tunnel in a burst of lethal energy. The universe seems to conspire against stable wormholes. General relativity allows for their existence mathematically, but nature appears to abhor them. Any attempt to prop one open would require titanic amounts of exotic matter, something we've never observed naturally. Even if we somehow conjured it, quantum effects near the wormhole's throat might destabilize it further, turning your shortcut into a death trap. In 2019, physicists simulated what would happen if a single photon traveled through a microscopic wormhole. The result: the wormhole imploded violently, its walls recoiling like a snapped rubber band. Yet the most unsettling possibility isn't collapse, it's corruption. Some theories suggest wormholes could act like cosmic prisms, scrambling the quantum states of anything passing through. You might emerge intact but changed, your atoms reconfigured in ways that erase memories or alter consciousness. It's a chilling trade-off. The price of bending space-time might be losing what makes you you. For now, wormholes remain hypothetical cosmic what-ifs that tease us with their potential while guarding their dangers fiercely. They're reminders that the universe doesn't offer free lunches, not even for light-speed travel. Every shortcut comes with a warning label written in the fine print of physics: proceed at your own peril. Primordial black holes sound like relics from a cosmic horror story, ancient, invisible, and potentially lurking all around us. Unlike the colossal black holes born from dying stars, these hypothetical terrors might have formed in the first chaotic seconds after the Big Bang, when the universe was a seething cauldron of unimaginable density. Imagine entire black holes no bigger than an atom, yet packing the mass of a mountain forged in the furnace of creation itself. Some could still be drifting through space today, silent and undetectable until they brush against something or someone. Now picture one passing straight through Earth. Even a primordial black hole with the mass of a small asteroid would unleash havoc without ever slowing down. The size of a proton but weighing billions of tons, its gravity would tug on our planet's crust as it zipped through at hundreds of miles per second. The result, earthquake swarms radiating along its path, volcanic systems jolted awake, and tsunamis triggered by the sudden displacement of oceans. In 2019, researchers modeled this scenario and found that even a fleeting encounter could release energy equivalent to detonating millions of nuclear bombs, not from impact but from pure gravitational distortion. But why haven't we found these mini-monsters yet? Their very nature makes them nearly impossible to spot. Too small to devour stars visibly, yet too massive to ignore. Primordial black holes might only betray themselves through subtle fingerprints, fleeting bursts of Hawking radiation as they evaporate, or the way they bend light from distant stars like cosmic thumbtacks pressing into spacetime. Some scientists speculate they could even be the elusive dark matter we've been searching for, their collective gravity shaping galaxies without emitting a single photon. The most unsettling possibility, they might be closer than we think. If primordial black holes exist in significant numbers, the solar system could be swimming with them, each one a potential rogue bullet. A direct hit is statistically unlikely, but over billions of years, even improbable events become inevitable. The universe doesn't need planet-killing asteroids or gamma-ray bursts to remind us of our fragility. Sometimes all it takes is a speck of concentrated nightmare left over from the dawn of time, passing unnoticed through your living room. Yet these ancient specters also offer tantalizing clues. Detecting one could unlock secrets about the Big Bang's earliest moments, testing theories of quantum gravity and the birth of spacetime itself. They're reminders that the universe's greatest dangers and its greatest revelations might be hiding in the smallest, darkest corners. Before the first stars flickered to life, the universe might have birthed something far stranger: dark stars, colossal behemoths fueled not by nuclear fusion, but by the annihilation of dark matter. Picture a star so vast it could swallow our solar system whole, its core simmering with particles we've never seen, tearing each other apart in silent, invisible fires. These theoretical monsters, if they existed, would have been the universe's first light eaters, glowing faintly with the heat of a mystery we still can't solve. Dark stars defy everything we know about stellar physics. Instead of fusing hydrogen like modern stars, they draw energy from weakly interacting massive particles, WIMP, colliding and self-destructing in their cores. This process would release a steady, eerie glow, sustaining the star for millions or even billions of years without ever igniting fusion. The result? A star that shouldn't exist by today's rules, ballooning to sizes incomprehensible next to our Sun. A single dark star could grow to millions of solar masses, dwarfing even supermassive black holes in sheer volume. Its surface would be colder than a campfire, yet its gravitational reach would stretch for light years, bending entire galactic neighborhoods into submission. Now imagine one surviving to the present day, lurking in some distant corner of the cosmos. Its sheer mass would warp the fabric of its host galaxy, distorting the orbits of stars like a spider at the center of a trembling web. Planets orbiting too close wouldn't freeze in the dim light, they'd be crushed by tidal forces or bathed in strange radiation from decaying dark matter. And here's the most unsettling part: we might not even recognize it as a star at first. To our telescopes, it could look like a gap in space, a shadowy void where light itself seems to vanish. Yet dark stars aren't just cosmic anomalies, they're potential keys to unlocking dark matter's secrets. If astronomers could find one, its spectrum might reveal the fingerprints of those elusive particles, finally confirming what the universe is truly made of. Some researchers even speculate that dark stars could have seeded the supermassive black holes we see today, their cores collapsing into the monsters that now lurk in galactic centers. So while they remain hypothetical, dark stars remind us that the early universe was a laboratory of extremes, a place where the rules weren't just broken, they were rewritten in the dark. And somewhere out there, one of these primordial giants might still linger, a relic from a time before light as we know it had even begun to shine. Blazars are the universe's particle cannons, active galaxies with supermassive black holes at their cores, launching jets of plasma and radiation straight at Earth with terrifying precision. Unlike quasars, whose energy sprays across the cosmos indiscriminately, blazars take aim. Their jets are cosmic sniper rounds packed with protons accelerated to near light speed. Gamma rays more energetic than anything our sun could produce, and enough high-energy particles to rewrite DNA from across the galaxy. And here's the worst part: they flicker. A blazar that's quiet for centuries could suddenly flare brighter than a million suns, flooding our corner of space with a storm of ionizing radiation before we even see it coming. Take Markarian 501, a blazar 300 million light-years away. In 2014, it erupted without warning, doubling in brightness in just 48 hours. Telescopes caught the outburst, a beam of gamma rays and cosmic rays so intense, it mimicked the aftermath of a stellar explosion. Now imagine that same flare happening 10,000 times closer, a blazar in our galactic backyard. The impact would be apocalyptic. Cosmic rays would punch through Earth's atmosphere like bullets, smashing apart nitrogen and oxygen atoms to create cascades of secondary radiation. Skies would glow with artificial auroras as the planet's magnetic field scrambled under the assault. At ground level, mutation rates in plants and animals would skyrocket. Electronic systems could fail en masse under the particle barrage. But blazars don't just kill, they create. Their jets are nature's ultimate particle accelerators, far beyond anything we've built on Earth. The Large Hadron Collider can push protons to 99.9999% the speed of light. A blazar's jet does it effortlessly across distances longer than our solar system. Some theories suggest these cosmic rays might even play a role in cloud formation, their charged particles seeding atmospheric changes that ripple across millennia. It's a sobering thought. The same forces that could sterilize a planet might also have nudged Earth's climate in ways we're only beginning to understand. Yet for all their destructive potential, blazars are also cosmic lighthouses. Their light, stretched and distorted over billions of years, helps astronomers map the structure of the universe itself. By studying how their jets twist and fade, we've uncovered clues about black hole spin, the nature of dark matter, even the shape of spacetime. They're reminders that the universe's most violent phenomena often hold its deepest secrets if we're brave enough to stare down the barrel. So while we track asteroids and solar flares, the real cosmic threat might not come from something we can see. It could be a flicker in the data, a blazar waking from its slumber, its jet already locked on to us, a reminder that in the grand theater of the cosmos, we're not just spectators. Sometimes we're the target, drifting between galaxies like silent cosmic fog. Intergalactic gas clouds might seem harmless at first glance, just vast collections of hydrogen left over from the Big Bang. But these so-called dark clouds are anything but peaceful. Picture a hydrogen behemoth hundreds of thousands of light-years wide, so diffuse it's practically invisible until it collides with a galaxy. Then all hell breaks loose. These clouds act like celestial Molotov cocktails, dumping unimaginable amounts of raw star fuel into galactic systems, igniting chains of supernova that can burn entire regions of space to a crisp. Take the Smith Cloud, a massive hydrogen river hurtling toward the Milky Way at nearly 200 miles per second. Discovered in the 1960s, this colossal structure is 11,000 light-years long and 2,500 light-years wide, enough gas to forge 2 million suns. When it finally plows into our galaxy in roughly 30 million years, astronomers predict a firestorm of star formation so intense it could outshine the rest of the Milky Way combined. Newborn stars would burn hot and fast, their short, violent lives ending in supernova explosions that shred nearby solar systems with radiation and shockwaves. Entire stellar nurseries could be wiped out in the very act of creation, a cosmic frenzy of birth and death at scales we can barely fathom. The real terror lies in these clouds' unpredictability. Unlike a black hole or quasar, whose threats are visible from afar, intergalactic gas is nearly impossible to track until it's too late. Some could already be entangled with our galaxy, their tendrils spooling into spiral arms, setting the stage for bursts of star formation that rewrite the map of the night sky. Others might linger in intergalactic voids for eons before suddenly collapsing under their own gravity, igniting hyperactive dwarf galaxies that flare up like matches in the dark. Yet these clouds aren't just destroyers, they're also galactic lifeblood. Without fresh infusions of intergalactic hydrogen, galaxies would eventually exhaust their star-forming fuel, fading into cold, dark stagnation. The same influx that triggers catastrophic starbursts also sustains cosmic evolution, ensuring new generations of stars and planets have the materials they need to form. It's a delicate balance: too much gas too fast and a galaxy burns itself out, too little and it withers away. So while we think of black holes and gamma-ray bursts as the universe's ultimate killers, sometimes the greatest danger comes from something as simple as a cloud, a silent, drifting giant carrying either salvation or doom, depending on how, when, and where it strikes. The cosmos doesn't need malice to be deadly. Sometimes all it takes is a whisper of hydrogen in the wrong place at the wrong time. Somewhere in the cosmic dark, two black holes circle each other in a slow, deadly waltz, each one the corpse of a massive star, now locked in a gravitational embrace that can only end in catastrophe. These stellar mass black hole binaries are nature's ultimate doomsday machines, their dance of destruction playing out over millennia until, in a final violent moment, they collide with enough force to shake the fabric of spacetime itself. The first hints of these cosmic duels came not from light, but from the faint tremors they sent rippling across the universe. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting gravitational waves from a pair of black holes merging 1.3 billion light-years away. The signal, labeled GW150914, told a story of unimaginable violence: two black holes, 29 and 36 times the mass of our Sun, spiraling closer at half the speed of light before smashing together in a millisecond. The energy released was staggering: 3 solar masses converted directly into gravitational waves, briefly outshining every star in the observable universe combined. Picture the final moments of this cosmic tango. As the black holes orbit each other hundreds of times per second, their immense gravity distorts spacetime like a spinning whirlpool, flinging ripples outward at light speed. These waves aren't gentle, they stretch and compress everything in their path, warping the distances between atoms as they pass. By the time the black holes merge, their event horizons stretch into a single, teardrop-shaped maw before snapping into a perfect sphere, ringing like a bell in frequencies beyond human hearing. The newborn black hole recoils from the collision, kicked by the sheer force of the impact at speeds up to 3 million miles per hour, a bullet forged from pure gravity. But the terror of these mergers isn't just in their power, it's in their aftermath. The newly formed black hole doesn't settle quietly. It vibrates, shedding distortions in a process called ring-down, emitting gravitational waves that reveal its shape, spin, and even the nature of spacetime itself. Some collisions are so violent they fling the resulting black hole clear out of its host galaxy. a rogue predator set loose in the void. Others birth intermediate mass black holes, bridging the gap between stellar corpses and the supermassive giants lurking in galactic cores. What drives these pairs together in the first place? Some might form from binary stars that lived and died together, their cores collapsing into black holes that remain gravitationally bound. Others could find each other in the crowded dance floors of globular clusters, where close encounters fling black holes into partnerships doomed to end in mutual annihilation. And the universe is littered with them. LIGO observations suggest mergers happen roughly once every 15 minutes somewhere in the cosmos. Yet for all their destructive spectacle, black hole binaries are also cosmic gold mines. Each merger tests Einstein's theories under extreme conditions, probing the limits of general relativity. The gravitational waves they produce act like echoes from the warped edges of reality, carrying secrets about black hole spins, masses, and even the possible existence of extra dimensions. It's a paradox. These collisions, capable of erasing stars without a trace, also illuminate the deepest workings of the universe. So while we might never see the moment two black holes collide, we can feel it. The faint shiver of spacetime whispering across billions of light years, a reminder that even in the darkest corners of the cosmos, nothing stays still forever. The universe doesn't just create and destroy, it dances, and sometimes that dance ends with a bang so loud it echoes through the very fabric of existence. Deep inside a black hole's crushing depths, where gravity twists the rules of existence beyond recognition, there might be something stranger than oblivion, a Planck star. Forget the silent darkness we imagine lurking past the event horizon. Quantum physics whispers a different tale, one where spacetime itself rebels against infinite collapse. When matter is squeezed beyond the limits of classical physics, a cosmic bounce could occur like a spring compressed to its absolute limit, finally snapping back. The result, a singularity wrapped in a shell of unfathomable density, glowing with the trapped light of dying universes. This isn't science fiction, it's a daring prediction of loop quantum gravity, an attempt to reconcile Einstein's relativity with the chaotic quantum world. Unlike traditional black hole models where matter crushes into an infinitely small point, Planck stars propose a barrier, the Planck length, the smallest possible unit of space. Here, quantum forces push back against collapse, creating a brief, radiant rebound. Imagine all the mass of a collapsed star packed into a sphere smaller than an atom, yet shining with energy hotter than the Big Bang itself, not for eons but for mere instants before vanishing. Now for the real cosmic twist. What if our universe is nestled inside one? Some theorists suggest that the Big Bang itself could have been the rebound of a Planck star from a parent universe's black hole. It's a dizzying loop of creation, universes birthing inside black holes, which then spawn new universes in turn. The evidence, if any exists, might lurk in the faintest echoes of our cosmic microwave background, anomalies in radiation patterns that whisper of a universe before our own. But Planck stars aren't just mathematical curiosities. They solve one of physics' most vexing paradoxes, the black hole information problem. If black holes truly destroy everything they swallow, they violate quantum mechanics' sacred law: information can't vanish. A rebounding core, though, could preserve that data, encoding it in the very fabric of a new universe. The implications are staggering. Every black hole might be a cosmic archive, a library of lost realities sealed behind a quantum firewall. Of course, we'll never see one directly. By the time a Planck star forms, the event horizon has already locked it away from our view forever. Its fleeting pulse of radiation would be swallowed by the black hole's gravity, leaving no trace. Yet the idea lingers, haunting the edges of cosmology, a reminder that even in the universe's most destructive corners, there might be no true endings, only transformations too alien for us to yet comprehend. The universe as we know it could be living on borrowed time, not from black holes or supernova, but from something far more insidious, bubbles of an alien physics, silently expanding at light speed to rewrite reality itself. These aren't science fiction what-ifs, they're called false vacuum bubbles, and they stem from a terrifying possibility that our universe isn't in its true lowest energy state. Picture space like a frozen lake with our familiar physics as the thin ice. Beneath it lies an abyss of true vacuum, a more stable state where fundamental constants like the speed of light or the strength of gravity might have entirely different values. If a single patch of space somehow tunnels into this lower state, it would trigger an unstoppable chain reaction, a wall of annihilation rolling outward at light speed, leaving a universe unrecognizable in its wake. Inside such a bubble, the very laws of physics would rearrange instantly. Electrons might no longer orbit atomic nuclei, dissolving matter into a shapeless quantum soup. Gravity could invert, flinging planets and stars apart like shrapnel. Even time itself might fracture, its flow rewired into something alien, the worst part. These bubbles wouldn't just destroy, they'd replace. By the time you saw the bubble's edge, it would already be rewriting your atoms, no warning, no escape. Some physicists check for evidence of these bubbles daily. Why? Because the math suggests they're possible. The Higgs field, the same quantum backdrop that gives particles mass, is metastable, balanced in a precarious state that could, in theory, tip over. Particle colliders like the Large Hadron Collider hunt for clues, probing whether we're hovering above an existential cliff. Others scour the cosmos for bizarre anomalies, patches of space where light behaves oddly or particles defy known physics, potential signs that a bubble already passed through, leaving behind a wake of altered reality. Yet there's a haunting duality here. False vacuum decay doesn't just threaten, it illuminates. If such bubbles exist, they'd prove the universe is part of a vast multiverse, each bubble a separate cosmos with its own unique rules. Our universe might even be the product of an older bubble's expansion, born from the collapse of someone else's physics. It's a cosmic Russian roulette where every click of the hammer might spawn a new reality or erase one forever. So while black holes and gamma-ray bursts dominate doomsday scenarios, the true existential threat might be quieter. A single quantum fluctuation in some distant nebula could already have triggered the cascade. The universe doesn't need malice to end, just a deeper stability lurking beneath the surface, waiting for its moment to rewrite everything. From gamma-ray bursts scouring solar systems clean to rogue black holes drifting unseen through the cosmos, we've faced down 25 of the universe's most terrifying entities, but which pose the most immediate danger to Earth. At the top of the threat list sit gamma-ray bursts, nature's ultimate snipers, capable of sterilizing planets from thousands of light years away. A direct hit would strip our atmosphere bare, leaving nothing but scorched rock in its wake. Close behind are quasars and blazars, their jets of radiation acting like cosmic flamethrowers, though thankfully, the nearest active ones remain comfortably distant. Supernovas earn their spot, two stellar explosions powerful enough to bathe nearby systems in lethal radiation, with historical records suggesting we've had some close calls. But not all threats are created equal. While neutron stars and magnetars wield unimaginable magnetic fury, their narrow beams and limited range make them deadly only to those unlucky enough to cross their path. Rogue planets and hypervelocity stars, though chaotic, move slowly enough for detection, giving us a fighting chance to adapt or avoid. Then there are the speculative horrors, primordial black holes hiding in the dark, cosmic strings lurking in spacetime's fabric, vacuum decay bubbles rewriting reality itself. These remain theoretical, but their potential for catastrophe keeps physicists awake at night. Yet here's the silver lining: space is vast and time is on our side. Most of these cosmic monsters are light years away or operate on timescales longer than human civilization. That distance grants us something precious: the chance to learn, to prepare, perhaps even to outmaneuver the universe's deadliest forces. Every telescope we build, every probe we launch is a step toward mapping the minefield of our galactic neighborhood. And who knows, one day we might not just survive these threats, we could harness them. Imagine tapping a magnetar's magnetic energy or riding a hypervelocity star's wake toward new frontiers. So as we stare into the abyss, remember, the universe isn't just a catalogue of doom. It's a challenge, a puzzle, and an invitation to push further than we thought possible. Now, over to you, which cosmic danger sends a shiver down your spine? Is it the silent creep of vacuum decay, the blinding fury of a gamma-ray burst, or something else entirely? Drop your thoughts in the comments, and let's keep the conversation as boundless as the cosmos itself.